Okay, now if we look our notes, I think our notes before is really black, not really clear here, but we are talking about inverse here. So basically what inverse means is we are going to exchange, let me just review a little bit. So inverse, this will be exchanging domain and range, right? In practice, basically what you are going to compute when you need to find the inverse is you are going to exchange usually x and y, but it can be happen in another function as well, as long as you keep consistent. So you need to solve in terms of x, and then you can change at the end x with y. But we can also visually means uh, reflecting function. Let's say reflecting functions through or about line y equal x. This is also one of the practice or visuals. If you have a graph, the inverse means you are reflecting your graphs through y equal x. Okay. Right? Okay. Okay, now we are going to move to the last part on this function. It will be about the logarithm. Okay. Okay, so logarithmic functions. Okay, we start with the exponential f of x, b with power of x. B is a positive and not equal 1. Okay. We start with this. Okay. This is, of course, exponential, right? This is exponent. Exponent, B is the base. So B can be any number, positive number, 2, 3, 4, and so on. Okay. Or even E, we decide to define E as 2.7818, something, right? Okay. Of course, by take this b or the exponent b with power of x, we know that this b of x, b with power of x, it's either, if you see the function itself, if you see from the left to the right, it's always increasing. But if you see from the right to the left, it's going down to the x-axis, right? Now the definition from this log, okay, definition for the log, uh, definition for logarithmic. Before definition, maybe we can just take a look this exponent. If you take the horizontal line to test whether it is 1 to 1, it's only crossing one point. So which means that this whole thing is 1 to 1 function. So this is 1 to 1 function. So by 1 to 1 function, it means that it does has an inverse. Okay. So conclusions, the power of x has an inverse. Okay. By these facts, we can write down so first definitions as in within the inverse terms for the logarithmic functions. we can say that the inverse of b to the power of x, or let me write completely with the function, is called logarithmic function with base b. And we denote this by writing the log with base b as log, and then write b as like a subscript. And then by definition from the inverse, if we remember correctly, if this is the definitions, then if we take the function itself, this will be equal to x. And then if we have log base b of x is equal to y, then we can also write in terms of exponent, this will be the result. So if we write the functions that is b with power of x, the inverse of this function should be the log with base b and x. This log, we can say, we say that log with base b of x. Okay. So log is another another visualization. Another visualization when you have some base that is the core of your multiplications. Okay. The core of multiplication, for example, 2. If you have power with something, you need to multiply 2 around n times. Okay. That's the meaning. So the log basically is saying that when you have some basic numbers for its multiplications, log is saying that you will have different scale, okay, different scaling. For example, usually we say the default in our base is 10. So we say that if we write log and then maybe 100, this saying that there is something here that is by default is just 10. Do you know why? Why is 10? Why is 10? Have you thought about it? Why is the number is 10? Yeah, why it's commonly used? Why people decide to use this base of 10?
Because we have the decimal system for counting.
Yeah, it's related to countings. Okay? You know, maybe if we have maybe another civilization, another planet aside from Earth, that maybe their hands is not with 10 fingers, maybe just 6. Maybe their computation will be different. Okay? Because we are so natural with 10 in our countings, it will be in our nature that 10 can be easily to be counted on. Okay? That's one reason. Okay? There are, I think, some videos explaining about this base things in a really simple way, in a different calculations. It's called, just let me just, this is just FYI. If you want to look in, I think in YouTube they have. you can look on the exploding dots. This is another way to look mathematics. So they define how to compute like addition, subtractions, multiplication, division with different perspective, and based on that, we can actually easily change the base. So when we're counting, we can change the base. It's difficult to explain, but you can just watch. It's like several videos. Each video is maybe around 10 minutes, 10 minutes, or maybe 6 to 10 minutes. If you're curious about the base, you can watch this exploding dots. The speakers has a really thick Australian accent, so but it's funny. It's funny. Okay, back to the log. Okay. Now, because of this, we can have some several property from this log. Or maybe before that, um, let's say in our graph, another thing about the scaling is if we maybe having some statistics or some data sets that has meaningful data on maybe every 10. But of course, if I write this, it seems wrong, right? The unit seems wrong, which we need to make it a little bit larger. So let's make it larger. So maybe this is 5. Oh, wait, 5. Maybe 1. Start from 1, 5, 10, then 15, 20. Well, this is your usual x-axis. But if your meaningful data is on maybe 1, and then 10, and then 100, the best way to look this data to analyze is making the log. So you can have really compact size of the data, and you can see how maybe you want to see the difference, you want to see how the curve fits with your data sets, and that's how the log will be useful. Okay? It helps you to do the scaling. Okay? Usually, maybe in temperature, maybe the difference with log also. Okay. Anyway, some property within this log. You have log b, and then this is b of x. This is actually equaling x. So we can also see this as this x goes by here. We can say that. And then the log b of b is basically saying that what power we need to take for b to become b is just 1. So it's equal to 1. Okay? Right? So that's why when we have this, let me just erase the arrow, log with base b of b with power of x, we can just say it's just equal x. Okay? This is for every x in all real number. Okay? Another property that is, I think, interesting is this property. This is for x positive. How this can be true, this is because if you remember the definitions with the inverse, let me write this for um, make sure that we understand the inverse. So if you have inverse, for example, this, this is true, we have done this last week, right? So what I mean by this inverse is because the log is the inverse of the exponent. So if we put the log inside the functions, for example, if we have, maybe let me write here. If we have the f is, what we can write here, this one, the b of b power of x. So let me write here. The inverse is log with base b power of x, right? So if we put either two ways, okay, we put this f prime x. Let's say we did the f prime f of x. So this means that f prime, let's just use the b power of x. The f prime is log b, so which means that we need to log b, and then we change with bx, like that. Got it? Okay. The same way for the other roots, which is f prime, f inverse, sorry. This means that we need to put in this log. Why? Is that correct? Oh yeah, it's correct. Put this inside here. Okay. I think just to know from the inverse, we can make sure that the log itself is correct. Although we can also use the log property, not the inverse, to also confirm that this is true. Okay? But I think if you know the inverse, that the inverse of the exponent will be the log, then we can just make sure that it's confirmed. Okay. 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 I think it's going to be here. Okay. Now, another way to see the inverse from this exponent is we can make our line, we line here, and write down that this is y equal x. And we can predict that the log, the inverse of this exponent, will be around here. To close. Yeah, around there. Okay. Just from the visuals, we can mirror the exponent, and that will be our log. Okay. Or let me give you the graph. Do I have the graph here? And then the interesting about the log, okay, if we try to use different base with different numbers, 2, 3, 4, and so forth, if we make the graph itself, we make the graph. Okay, what's the most obvious thing that you can find from the graph? From this graph, we have log with base 3, log with base 2, log with base 10, log with base 5. What's the most obvious thing from this picture? Yeah, they all crossing x equal 1, right? They crossing the same point here. They crossing this 1. right? So, which means every time they are uh, in x equal 1, they are at 0. Right? They are at 0, okay? And this is also important for the log, okay? The log property. Let me write here. They are passing x, or maybe let me just write the coordinates 1, 0. Okay. Some property that might be useful. I think some of you are already familiar with, but let me just write just to review some laws. Now you just write the conclusions, and if you want to confirm whether this is true, one way to prove this is taking the exponent, and taking the exponent form, and then change to the log. Okay. Okay, before we also mentioned about the E, right? The Euler number, okay? The 2.78 something. We can also include E in our log, and that is what we call the logarithmic natural or natural logarithmic. Okay. Right here, natural logarithm. So we can say that if B is E, then log E of x, we can just say that this become our ln. This means that the ln is log with the base E, okay? So if we have ln x is equal y, this means that y is, or sorry, it should be E with power of y. E with power of y may equal x. Of course, all the logarithm law will be also applicable within this ln. So when you have ln e with power of x, this is equal x, and x is all real number, and e with power of ln x also equal x. We can also prove this using the inverse. So if we set the ln, if we set the x equal 1, then the ln e is equal 1. Okay. So we can write here that ln e is equal 1. But this is practically saying that this means that log e e. That's why it's equal 1. Okay. The same thing what we did with the another base. Okay. So what you need to remember here is when we talk about e, it's not a variable, it's a constant, it's a number. Okay, e is a number, okay, a rational number. which we define the number as 2.781818, and etc. with the long decimals. I'm not sure. Even many researchers or many mathematicians, I think they have found maybe around hundreds, or maybe around hundreds behind the decimals for the numbers e. So we don't know after that what kind of numbers. Okay? Another property is x with power of r, e, r, ln x. Well, this is actually it's like playing a puzzle. Okay? When you get one consistent formula, you can make everything. This is if you think from this. Okay, so you can write this as, and you know that this whole thing will be x. So we can say that this will be x power r. Okay, do you get the logic? Okay. So every formula here is actually came out from one or two consistent formula at the beginning. So if you can just keep one or two, you can make out the others. Okay. Okay, one more thing about the log before we move to limit is one more thing also about the inverse of trigonometric. So one more thing about log, go to the inverse one more time and then go to the limit. Okay. Okay. The other thing that is important is the changing of base. This is quite common in log. So whenever let me write for positive number b, which is b is also not equal 1. If we have this log b of x, we can exchange this and we can say we change the base into e. Okay? If we can change the base into every number, a positive number actually. Okay? So for example, we can change to e, ln x, ln b. We can make that. But actually, this came from, let me write the logic here. This came from the log x divided by log b. So we have some base here that is still can be every base. Okay, can be every base. If we change to base 3, it's okay because with the same logic, you will cancel out those base. Okay? So you can make out in any base you want. For example, you can use the e. Okay. Well, if you would like to know how we can make out this this property, we can, maybe we could start with the equations of log. Okay, start with this. And then we know that the b with power of y is equal x. Okay. And then from here, let me write at the bottom here. take ln both sides. And then move this y to the front. This becomes y. And again, this ln can be every log with any base. Okay. Okay, one important here, I forgot to tell you. Within the log or ln, or maybe log in the general, you will see that the domain, it will never be negative, right? So if we look here, this negative is not appear in our log. Okay, that's just one thing to note. Okay, so if we have log with something here, this should be, if there is any x or y or any variable, this should be greater than 0. Okay, the domain. Okay, perhaps anything to discuss? Any confusions? Any confusions? No? No? Okay. Okay, the next, I think this should be the last thing on the functions. Inverse of trigonometric. I almost forgot this one. Okay, now let's begin with the graph. Let's say we begin with the sine. We begin with sine. So y equals sine x. Okay. Okay. We have horizontal line, and of course, with this horizontal line, we know that these functions will be. This is horizontal line test. We can write that these functions, the sine, is not 1 to 1, okay, because of the horizontal line test, right? But if we make some restrictions on the domain, okay, if we make restrictions, for example, we restrict from this negative pi over 2 until pi over 2. So we restrict the domain. So we restrict restrictions on domain. We make it from, okay, so domain only from negative pi over 2 until pi over 2, that will be our domain. Then, if we check with the horizontal, of course, it's a function that is 1 to 1. Okay? Then this part will be 1 to 1. Okay? And that's why the sign, in our case here, with the restricted domain, we'll be having an inverse. Okay? And we call the inverse of sine function, or we call with arc sine. Okay? So we call the inverse of y equals sine x is we call sine inverse x or arc sine x. Well, sometimes you write sine with e, sine and the e still the same, I think. Okay, now from the definition of the inverse, then if we have sine inverse equal y, sorry, should be sine inverse x. So this should be sine y equal x. And this y is start from the domain in x, right? Just remember, basically the inverse is exchanging domain and range. Okay? So the domain we restricted for the sine x, that will be our range. Okay? And the range itself in inverse is our domain. Okay? And the graph itself for the inverse will be this. It's sine inverse. Okay? Maybe make it a little bit thicker. Is my writing too small? Because of the system, I cannot make it the square cannot be larger. So I think I need to make my writing a little bit larger. And of course, all the things in inverse, the property will also can be applicable. And we can make sure that the domain and range are correct. So this will be start from this and and the same thing with cosine. Okay, I think I don't think to write the cosine. I think it should be similar to sine, just to shift a little bit. And also tangent inverse. Okay, I think domain will be the same, but for tangent it has the asymptote, right? It has some infinite points. But what I do like to take notes for you guys are if we have the expressions, for example, cosine and then tangent inverse x. What does it mean? Or how can we make this expression simplified?
We can write tangent as a sine of sine over cosine, yeah.
Mm-hmm.
Cosine square of
Really? The inverse is not reciprocal. It's not 1 over
it
something.
is sine inverse sine over inverse cosine, yeah.
Mm-hmm. But that means this is cos inside the cos, right? Mm-hmm. Okay. Let me give you one simple logic that it will be consistent in every inverse of trigonometry. Okay. Let me start with this. If we have the sine inverse x equal y, we can write sine y as equal x. Okay. If you remember that we can write a triangle to define the trigonometric. Okay. If we have sine, let me write sine y equal x, which means that y is our angle, right? Let's say our angle here. Okay. The sine, well, if you maybe still not convinced yet, I will also explain in the basic of math the same thing. But let me just explain first. The sine is here, right? Divided by here. Okay. The other side you can find through Pythagorean theorem. Yeah, it's okay, right? So the same thing here. If you have cos tangent inverse x, so what you are going to do first is just define with any variables you can. For example, y. Let's just define first this. Okay, define this, and then we define this as tangent y equal x. Okay, now we have a tangent. Okay, and then make a triangle. Write y here, the angle. The tangent is x here and 1 here, right? The Pythagorean makes this 1 plus x squared, correct? Okay. So this tangent inverse is y, so this is actually cos y. What is cos y? X over the hypotenuse, right? So we can write this become x over. So that's simplified expression from the cos tangent inverse. Okay. We will go with this kind of expressions later on when we are on differentiation on the inverse of trigonometry. Okay? And this is the basic expressions that really useful when you deal with the derivatives. And the other inverse for the trigonometric, the cosecant, secant, cotangent, I think I will skip that because that is basically have um, similar property with this cosine, sine, and tangent. Okay, any questions? Yes? Hmm? Which one? Oh, it's sine, right? If x, right? Okay. There should be one. Okay, good, good. Correct, correct. Yeah. If I'm writing x, that should be sine. Okay. Good, good, really good. Okay, it means that you're not sleeping. Yeah, eating. Okay, really good, really good. Yeah. I forgot. I thought that the sign here. Okay. Okay, and then that's all for chapter one. Okay. It's all about functions, uh, finding domain, exponential, log, inverse, right? And also the transformation, okay, how to shift the graph, reflecting the graph. Okay. Now we are going to move to the limit, okay, the chapter two. We are going to start with the tangent. Yes, the tangent. Okay, so let me. Yeah, I think we can have a break, okay, and then we can continue after the break. Let's take a break for a while. Okay, we are going back. Okay, let's go back from the dream world. Okay, came back to reality. Okay, so before I'm going to go for limit, uh, I'm just offering some students for tutor. So if you need tutoring, okay, I think you can find in the learning center. We have the digital learning center. You can find anything about tutor, or if you want to find tutor from your senior, like from GDEP, you have a senior that may be good for teaching calculus. You can ask him or her to apply for tutor. But I think the requirement, his grade for calculus should be at least, I think A. Yeah, I think A. So if you can find seniors and your seniors want to help, they can officially apply, and of course it will be recognized as a part-time. Okay, so it can also help you. Or if you want to join IFTP students, I have prepared one student to become a tutor as well. If you want to join, but that will be using English. But if you want to locally teach by your senior using Mandarin, I think you can find from your senior. Okay, if you have, okay, or if you want to join, you can join. But it's not yet started because I think we will start maybe next week or next 2 weeks, maybe next week, because they need to apply first, then need to arrange the schedule for the tutor. I think it will be effective tutoring, preparing maybe quiz and midterm. Yeah, that will be, I think, effective. Okay, now we move to limit. Okay, now limit, it starts with the concept of the tangent. Okay, the tangent. So first, what is tangent? Okay, so I also mentioned this. I'm not sure whether it's in calculus or in basic math, but basically what tangent means is, it's, if you know the words in English, tangible, tangible, and it's getting touch, or you can say this is touch. I think it's from Latin, Spanish, right? What is in Spanish? You say
The first four letters. Tan.
tan.
Tangente.
Tangent. Okay, okay. Yeah, yeah, yeah. It's to touch, okay, or touch, or to touch. Okay. So in math, what kind of touch that is meaningful? Okay. Of course, if we talk about math, we talk about precisions. We need to exactly know where the touch will be. Okay. The way we know is if we have a graph, and of course, if we draw a graph, then we have some rectangular coordinates, right? Well, depends on your drawing. The units can be the precisions of this unit. It's subjective unless you make with some software, right? So, for example, we can define this axis with this 1, 2, 3, 4, like that, okay? Or maybe smaller than this. That's also possible. But what I want to share with you here is when we have a graph in a rectangular axis, and we want to know, like in every dot in this line, the curve, the blue one, okay, this line is actually coming from many dots, right? We connect many dots and it become line, okay? So when we connect this, and the more the dots will be, practically it's become line, okay? Or in a sense, you can say like a pixels in your smartphone or in your display. like a pixel. It's actually like a dot, right? And you know the resolutions, like you have HD, blah blah, 2K, 4K. It's actually talking about dots. So when we talk about math, we talk about dots. So when we combine all dots, it's become line. And when we want to know exactly one dot in that line, for example, maybe here, and then we want to know, is there any line that is perfectly touch one point? And that will be our tangent line. That's the definition using visuals. Okay, so we have here, for example, in our case here, probably here. Okay. Of course, when we draw manually, maybe using paper or using digital like me, we are limited by our resolutions. Okay, you see that in some part, it seems that the blue line and the red line is stick together. But in reality, in math, it should be only one perfect point. Okay, that should be an easy way to know the tangent. Okay, so this is what we call the tangent, or in our case here, this is the tangent line. Tangent line, and we need to specify the tangent line where we need to specify. Maybe we take the point here, P, tangent line at point P. And that is one typical problem in calculus, that is to find the tangent line. Okay. And why the tangent line becomes important? Yes, yes. We will arrive on the derivative. But the tangent line itself is one way to say we approximately predict, okay, predict with some functions, we can make some approximation. Okay. Because you look the tangent line, you look point P, nearby this point P, the gap is really close, right? So in another way, that is one way to approximating some value. Okay, that is one useful of calculus method. So that will be our topics. I think next maybe several weeks from now, approximations, okay, using the line equation. That will be one of our sections. Okay. Okay. Now the problem is, how do we define this tangent? Okay. Now to get into more visuals, let me just give you a visuals. Let me just give you a graph. Do I have the graph? I have, but I don't have the, maybe here. Oh no, this will be the another one. Let me just draw the simple graph. Maybe using just our usual typical x squared. Can I just use x squared? Okay, let's say this is our y equal x squared. And then we have in point, we have maybe here, P. This is one point. Okay. And if we draw the tangent line will be around here. That is our tangent line. But the question now, how to define the tangent line? Okay. Consider that you don't know about derivative, about limit. Okay. If you know, forget for a while. Okay. Let me just start how we can find that. Okay. So first is we start with another point that is maybe around here. that is point Q. Okay, and of course this point Q, it can be any point, so we can take this point as just using our function x squared. So this point will be x and x squared. Okay, because Q can be in any numbers. Okay, so let's just take that. And now, suppose you know about the gradient or the secant. Okay, the secant is maybe let me draw with the orange color. Okay, I think I should make a little bit bigger. Okay, so let me just write here that what I want is this is the x squared. This is the secant. And this will be the tangent. Okay, suppose this is the same graph. Okay, it's a little bit different, but suppose it's the same. This is the P, and this will be the Q. Okay, now the idea is if we know that this PQ, we can make our ratio for its gradient, which means the gradient means we can take ratio between this triangle here. We can take this ratio delta y and delta x, right? And we can take the x squared and 1, the point, as our our distance. Okay, so we can write down this m pq is the delta y is start from x squared minus 1. From here, x squared here minus 1. Okay, and then over the delta x will be x minus 1. Okay, we call also this gradient as a secant line, which means the secant is something to cut. Okay, so we cut this curve, and that we call the secant line. Or let me write here, this is also called the secant line. And from here, what we are going to do is we can take some number of x and then compute the m. Okay, so for example, we can take number, let's say x is equal to, what's happened now is m will be 4 minus 1 and then 1, so it's be 3. Okay, and then let's take the x, take lower, maybe take 1.5, because you're gonna take 1 because it will be undefined, right? Let's take 1.5, and you can take the computations, calculate the m, will be resulting some numbers 2.5. Do the same thing, lowering the number, but not equaling 1, but with almost 1. Let's say almost 1. When you take maybe x equal 1.01, you will get some m, will be around 2.01 something. And when you take closer, and reaching almost 1, okay? Maybe you have 0.000000001. Maybe you can get some m that will be maybe 2.0000. Not sure how many zero here, but you can just make it as we'll be having some numbers that is going to be almost 2. Okay, almost 2, but it's not 2, it's almost 2. Okay, okay, that is from x equal 2. So let's say we move the q to the left side. Okay, so we start x from 0. If x is 0, then we will have -1 divided -1 is just 1. And then we increase this 0, almost 1. Okay, so we increase maybe 0.9 and we get some m, right? Maybe 1.9 something. And if we increase, almost reaching number 1, so x maybe 0.9999 blah blah blah. The m also getting 1.99999 something. Okay? From this phenomenon, what we are going to see is this m here and m here. We can say that it's actually getting closer to number 2, right? It's getting closer to m equal 2. Okay? So we need to have some definitions to make out that. I think we can make it 2. Okay, how about to make it 2? So we need to have some. I think it's a kind of compromise, but it's useful for simplifying the formulation or computations, and that's how we define limit. Okay, so limit is actually something that really close, but it's not that number. You see, we have 0.00001, or we have 1.99999. It's almost reaching 2, but it's not 2. Then we need to have something to say about it. And that's how we say limit. Okay? So that's how we get limit. So from here, we say that limit, okay, as maybe Q getting closer to P. Okay? So Q can be from the right, from 2, getting to 1, or getting from the left, from 0 to 1, of the m of PQ is our original m. In another word, in our case, this MPQ, we can say that as limit getting closer from x to reaching 1, from the m is x squared minus 1 divided by x minus 1, from our trial and error is equal to 2. We are not using any limit computation yet. We're just using some trial and error from some numbers. Okay, and this is what we got. Okay, and that's how we are using the worst limit. Okay, the worst limit to define something that is closer to. Or let me say a concept of getting closer. Well, this is my oversimplification words, but from what I've been told you, that is how it is. Okay, the limit. So this tangent problem, or tangent and secant problem, can also be explained with some physics phenomenon. I think the most obvious way to look is probably the distance problem, when you have some velocity, some accelerations. Okay, we can make this tangent problem maybe can be understood really well from this physics. I will explain later. Okay, let me just give you the visuals. What we have here. Let me just take the picture. Okay, now what we did is precisely these two methods. The first is we have point P that we want to getting close to, and we have the Q that we are going to move. Okay, so we start maybe from here. Okay, from here, let's say Q is up there. Okay, the secant, and let's say we are going to move Q as close to P. Okay, so we move Q, and then maybe here. Okay, so as Q getting closer to P, you will see that the secant line is also getting closer to the tangent that we are going to evaluate, or we want to make out the formula. So here is the close one. So if you can imagine, if Q is maybe getting closer, maybe here, since we have some restriction in our pixels, you will see that it's kind of touching each other. So, but remember, in a limit, when you deal with limit, it is actually it's not going to be the same as its number. Limit has some certain gaps. Okay, like I told you before, maybe 0.00001, really small gaps. Okay, so when we deal with limit, it's just to say that we simplify the calculations. Okay, to ignore the small gaps. That's it. The limit really is. Okay. Okay. Now, if we look the other way, maybe Q is from the left side. Seems very far, but when Q is getting closer, to the right, to the P, we move. Okay, I think we can continue. I'm just changing the platform. But now the online class is we have a problem with the connections, and it's I think the server is have a trouble as well because of the connections. So I will just use my notes here. Okay. So let's just recap what we have. So we did the getting closer from the left, getting closer, and then getting closer, and eventually, similarly with the previous one, is getting closer and closer, and making this blue line is getting in touch with the red line. Okay, that's the point of the limit. Okay. And then what else? Okay. And now if we look on some situations that might be useful for our case, okay. If we have like a physics problem, if we have a ball is getting dropped from the height maybe 450 meter. Okay, this is the ground. The question is asking what is velocity of the ball after 5 seconds. And now we need to understand first what does it really ask? Okay, so we have a ball here. We have a ball. It's dropped. Okay, the ball is dropped. Okay, drop. Okay, and it's going down here. But the interval for the time is just telling you that it's what is the velocity after 5 seconds. Okay. So the problem here is it's just giving you that the 5 seconds is maybe just a single time. Okay. So we are going to look at what if we have some interval. Okay. So again, this will be related to what we have done before. We have the limit, right? We have something that we are going to getting close to. So let's say we define first average velocity. Average velocity, it depends on the positions, okay? How it changed. Okay? Let's say that we define this as change in position. Change in position divided by the time elapsed. So time elapsed, we need to define the interval, okay, of time. For example, we know that the time is supposed to be after 5 seconds. So let's say we decide to have t equal 5, and we need to define maybe t equal 5.1. Let's say we have some interval 0.1. Okay? Let's say we are going to consider, okay, T1 is 5, T2 is 5.1. So we have some 0.1 as interval. Okay, let's say we have that. So the average velocity, let me write average velocity, is change in positions. Let's say the function of positions, we can write d or s. So let me write just s. So 5.1 minus 5. And divide by 0.1. And let's say, I forgot to mention, we define also from some experiments, it's Galileo experiment. So from observation, let me write here, from Galileo observation, that he write that the distance or the position, function of positions as a function of time is equal 4.9 t squared. Okay. Let's use this formula to get to our positions. Okay. So this 4.9 t squared we are going to include in our calculation here. So we are going to have and then you can use your calculator to compute, and this will be around 49.49 meter per second. So that will be our average velocity. But what I want to tell you is not the final result, but how about we change our interval? Okay? We change our interval. So let's say the interval that we count here is from 5 to 5.1. We get the velocity is 49.49. Okay. if we make the interval smaller, okay, so this is 0.1. If we make it smaller, so we take 5 and we take 5.05, we will get this getting also smaller, probably around this number. And if we make even smaller, of course you can also try to prove the number with, if you bring your calculator, it's also getting smaller. And when we make one more smaller, make another decimals, 0.001, we take this as 49.0049. And you can predict, you can imagine when we have maybe smaller than 0.001, it will be getting closer to number 49. Maybe it would be 49.0000 something. This is just to prove that the limit also can work in these situations, in this case, okay? And we can define, okay, when we have this kind of results, we can define that what we did here, when we're limiting our value, the velocity is not just average velocity, but we are going to make that instantaneously at t equal 5. So we can say that when t equal 5, or we can say that the interval from 5 to something that is really, really small, with concept of limit, we can say that when t equal 5, we say that this will be our instant velocity or instantaneous velocity. And this is due to limiting value of average velocity. So this is practically what we have done before. We try to make the secant line getting closer to the tangent line. This is what we have done before. So we are getting closer from the average velocity, getting closer to the instant velocity. So the instant velocity is our tangent. It's our tangent. So this is our tangent. Okay. So what we did here is actually taking the same problem. So this is, let me visualize what we have done. So this is the functions s equal 4.9 t squared. And we define 5 is our t, and q is our any interval that we want to make. Okay? It can be close, hard. But what important here is the secant line here is our average velocity. Okay? Average velocity. What we want is the tangent line here. Okay? So we are going to move q, getting closer here, which means the interval is getting closer, getting smaller. Okay? The interval getting smaller. So this is what we want. So when this secant line from q getting close to this red line, that means it's getting close to what we have, or what the question is asking. It's asking the instant velocity. Okay. Okay, I think I will stop up until here. But I would like to have some feedback as usual. So if you don't mind, after this we will have some a little question answer. Okay? Maybe questions first if you want to ask something. So far okay? So far okay? Okay. Okay, let me go through